Ideal for axial.
That's the end. So, has anybody broken anything in class yet? Nobody? I remember once on the first day, about 3-4 terms ago, it's the reason we use the torque wrench to tighten the vise in the milling exercise on the first day now. The torque wrench with the long handle. Apparently the instructions didn't clearly indicate that after putting the part in the vise, you should tighten the handle. And apparently the PLA that was leading the exercise didn't clearly indicate that after you put the workpiece in the vise, you should tighten the handle. And so it's the one where the bottom of the Y block is sticking up and the giant face mill comes around, running marginally too aggressively because we want you guys to be impressed with the chips flying at you and bouncing off the glass. It's on purpose. Also, we want it to go quickly. And if we go slower, then it won't be as quick. And yeah, so they did put their part in, closed the door, pressed go, and we bought a new window that next day because it threw the part out right up against the window. A clear example of insufficient clamping force. If you go back through this video, actually, and let's look at a couple of them. It was, all right, replay. All right, what happens here? Oh, so what happened? The tool was going around the workpiece, right? The workpiece came out of the vise and broke. I happen to know that on, you guys have seen the mill drill center. It's right as you walk into 108. It's next to the lathe, big boxy-like machine. I happen to know that the belts, that's a belt-driven machine. There's a servo motor. There's a belt that comes over to the spindle. Happen to know that those belts cost $1,000 to replace. I know they cost $1,000 to replace because we've replaced them more than once because parts have pulled up out of the fixture like this. And if you do it just right, when the part pulls up out of the fixture, it stops the motion of the spindle. Right? You could picture that. You can sort of feel that. Well, you can feel it. You can feel it when it shakes the floor. It stops the motion of the spindle so fast that the motor can't stop that fast. The belt is the weak link in the system, which is actually pretty good because the motor would have been like $6,000-$7,000, and the spindle probably $10,000 for the spindle unit. So we don't want to replace those. Insufficient clamping force. Insufficient clamping force, right? And so what causes there to be insufficient or what causes the part to come out when we have insufficient clamping force? Yeah. Yeah. The cutting force, right? So let's, I got actually a WPI student example of some insufficient clamping force that we can look at. So this didn't happen at WPI. It happened a few months after he graduated and went to work someplace. The workpiece was a large piece of steel. The tool came in to do its cutting operation normally. They miscalculated the pressure. So these are hydraulically actuated clamps on these. I don't know if you've noticed that. You press the foot pedal and it opens. You press the foot pedal and it closes. And you hear that noise when it does that. That's the hydraulic pump working to pressurize that and squeeze those together. And so you can adjust how much hydraulic pressure you use. And so they had inadvertently had the wrong hydraulic pressure, large steel part, spin. Oh, you know those spindles in these Haas lathes, they go like 6,000 RPM? That's pretty fast. We don't let people run our lathes that fast. You know why? We'd like them to not can opener the back of the machine with their workpiece when it comes out of the fixture. So through the steel sheet metal in the back of the machine. Well, let's think about it, right? We spent last week talking about energy. So if you've got that mass of steel rotating, how much energy is in it? It was rotating, is it like half mv squared or something like that? Wow. Yeah. That could be a lot of energy if it's a heavy piece of steel. There was an MQP a few years ago. They were building an energy storage device. And they had an 18-inch diameter steel plate about an inch thick. So maybe 100 pounds, 90 pounds, something like that of steel. And they wanted to put it on a shaft. They were at our shop because they wanted to put a hole in it to put it on a shaft so they could spin it as a flywheel to store energy. My first question was, how fast are you going to spin it? 1,800 RPMs. I says, where are you doing your experiment? In a lab in Higgins. Good, not here. That's my thought initially. And then I said, can you please let me know which day you're doing your experiment in the lab in Higgins so that I make sure I'm not walking down the hallway when that piece comes through the wall. Right. We will actually, this week we have a homework problem where we calculate energy. And we calculate the energy of, who's ever used a manual lathe? And so did it have like a manual scroll chuck? So in these manual lathes, who's used a drill press or a drill? Yep. You know how if you use like a cordless drill or something, it probably has a speed chuck on it. You hold on to it and you pull the trigger and the thing opens and closes. Well, there's a kind where you turn a little handle to open and close that too. That's sort of how those manual lathe chuck keys work, is you put it in the chuck, you turn it. We have a rule here. If you take your hand off of it while it's in the chuck, you are asked to leave and never invited back. You're done. We used to use them in ME1800. If you did it during ME1800, you failed. No exceptions. Because, well, I've seen one of those stuck in the concrete ceiling above the lathe. When you start the spindle on the lathe, and it gets one full rotation before it loses enough friction that's holding it in there, and it flies out. So that's what we'll calculate in the quiz, is how much energy does that have when it strikes you in the forehead? It's enough to kill you. Okay. All right. So I don't know if you noticed this when you were on the MFE Labs website or not, but we do have an email alias. I broke this at WPI. Since nobody in the class has broken that, nobody's been told to go send an email to that. But I guarantee somebody in your course of using the facilities will break something. Guaranteed. So when you do, email ibrokethis@wpi.edu. Tell us what you were doing. What was the result? Please include pictures. What is the approximate cost to WPI for your mistake? Because we don't make you pay for it. Once we told somebody we were going to make him pay for it. But it wasn't because of the thing he broke. And it wasn't because of the cost of the thing he broke. It was because he used a forged building master key to get into the lab, which was bad. But not nearly as bad as the fact that after he broke the thing, he tried to hide the fact that he did it instead of just telling somebody, hey, I screwed up and I broke this. So we did tell him he was going to have to pay for it. We did send the police to his apartment to wake him up the 2 days before graduation or something like that. But we didn't make him pay for it. I broke this WPI. What's the approximate cost of WPI for your mistake? And what are you going to do next time to make it not happen again? We read these. We review the answers. If we don't like your answer to the fourth question, we make you have a meeting with us. We invite you to a meeting before you're allowed to use the facilities again, so that we can make sure that we actually understand what it was that happened and why that broke, so that we don't repeat it again. We use that information. You guys use the operator checklist in lab? We use the information we collected from those surveys to create that operator checklist. So is there a common trend? Is there something that commonly makes things break? And can we fix a policy to make that go away? Right? I figure it costs us about $90,000 in repair bills to create that checklist. And since we've been using the checklist, we have not had a single crash that couldn't be attributed to somebody skipping one of the steps on the checklist. So don't skip the steps on the checklist. Okay. Let's see. Insufficient clamping force. All right. That's one of the things that fixturing is about, right, today? Yeah.
Oh, yeah.
Go for it.
No.
No? Okay.
No.
Forget he said anything. How do you know when it's about to hit the fan? You're standing in front of the machine tool. How do you know if it's about to hit the fan? You get your hand up. You feel a vibration that suddenly appears. Maybe you get your hand on the machine, you feel the vibration start. Maybe you feel the vibration in the floor, because it could happen. Yeah.
Aggressive noises?
If it sounds bad. I've frequently and it's kind of fun to do with inexperienced operators. When you got an inexperienced operator at the machine, and you've set it up for them, and you've told them, you know, when the parts are done, take the part out, do this. And then you walk away, go somewhere else to do some other high-value work. As you're walking away, you say, if you hear any bad noises, press the big red button. I wonder if there's a class over there now. Right? Now, what happens if we press the big red button on the machine, the E-stop button? Everything stops. Right? It actually applies a brake to the spindle, and it stops the spindle as quickly as it can. It stops the XYZ motion. All the XYZ motors stop instantly. It doesn't power the machine off. It actually stops it. Now, there's big red buttons on the walls in the lab, too. Anybody know what happens when you hit one of those? Turns off the power to all those machines. Now, if we turn off the power to the machine, it doesn't stop. It continues to wind down. And if we've got our 80-pound piece of steel in it, it's going to wind down for a long time, because they like to put good bearings in these things so that more power gets from the motor to the chip, right? So, okay. So if there's a bad noise and it's not your machine, what do you do? Hit which E-stop? There's the Urmi Stop and there's the machine E-stop. If you can hit the machine E-stop, hit the machine E-stop. If it's more than like 2 steps away and you're right next to the Urmi Stop, hit the Urmi Stop. It's a judgment call. Several years ago, my annual physical at the doctor's office, he says, is there anything else you want to talk about? And I say, I get this pain in my shoulder and it just doesn't go away. It's like this ache in my shoulder. So he like moves me around and does stuff like this. And he says, well, it's sort of like tennis elbow, except it's a repetitive stress injury that comes from making this motion. And I'm thinking, I just start laughing. And he says, it could happen from a single instance. And I'm thinking, well, I mean, Nazi camp was a long time ago. I don't think it was that. I never went to Nazi camp. Although I do have the haircut for it. And I just start laughing. And he says, oh, you remember the incident? And I says, well, no, I spend about half the day doing this, diving for the emergency stop switch on the machine tool, trying to weave between the students, right? And that day I stopped because the machine's a lot cheaper to replace than my shoulder. But yeah, so it's never, so you hear a bad noise, press C-stop, right? You ever see somebody running the machine and they're looking through, especially on the lathe, you know the little tiny windows on the lathe? Why? Yeah.
Part comes flying at the window, a smaller window is going to hold up better.
Smaller window is going to be stronger in general. That sheet steel next to the window is going to be stronger than the window no matter what, right? In fact, this one, it bounced off the window. It went back and came out through the back of the machine. The paper you see there is covering up the broken glass. So you ever see anybody running the machine, peering through the window like this? Have you ever seen that? Don't walk up behind them and start talking to them. Let me turn this thing on. Right. Document camera. Yeah, so don't walk up behind them and start talking to them. They obviously think something might be just about to crash. Right? Hear a bad noise. See something move that's not supposed to move. Right? You look through the window. You're watching the part. If you see it start to vibrate, something's bad. If you see it start to move, something's bad. You can, if you're quick on that e-stop, you can frequently save the tool from breaking. The workpiece is usually done, but you can frequently save the tool. Yeah. All right. Aluminum does not make sparks when you cut it. If you see sparks, you are now cutting steel. If you're intending to cut an aluminum workpiece and you see sparks, you are now cutting the machine. If you see sparks, press the e-stop, unless you're cutting steel and you intended to see sparks, and then you got to use your judgment. Yeah, sparks. If you're using the lathe and it suddenly sounds like an old Vietnam War movie and the helicopter's coming in, thump, 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 thump. That means you're cutting the little 3 pieces that come out that hold the workpiece, which are part of the machine tool. If it sounds like a helicopter and you're not intending to have an interrupted cut, press the stop. What else we got? All right, let's get into fixturing. What's the purpose of fixturing in CNC machining? Somebody stop me when we have 10 minutes to go, by the way. This is that room where I can't see the clock. Okay, I got plenty of time. What's the purpose of fixturing in CNC machining? Why do we fixture parts? Or why fixture? We just spent some time talking about it. Okay, more basic than that. Yeah. Yeah. So we've got to counteract, we use engineering terms, right? Counteract machining forces. So counteract machining forces, that is one reason that we fixture stuff. Why else do we fixture in, actually in any instance where you fixture, so it doesn't have to be CNC machining, it could be in painting. We fixture stuff for painting. In a coating application, we fixture stuff there. Why do we fixture? Yeah. To counteract machining forces so that it doesn't move. We got that one. Why else? Yes. And you're David, right? Okay, David. So that you're only working on what you're intending to work on. I think I know what you mean. That's like why we set the work offset and stuff like that. So yeah, that's not what I mean though. You're not incorrect. We do only want to work on what we're intending to work on. What do you got? And what's your name? Sam. So it orients the part. Is that what you meant, David? Kind of? Yeah, I kind of think so. It's just not the words I wanted you to use. Anybody else? What does it do besides orient the part? Yeah.
Some of them don't move the part.
So you fixture it to the table, and then the table moves like this. So it allows you to do that relative motion. Sure. That's not what I mean, though. Yeah, we don't want it to move. And we used to make a different version of the Stirling engine in ME1800, and the version we did had a flywheel. So there was a round part that we machined on the mill because we had to put some features on the face of it. And one day I was setting up the machine. And it's always bad for me to be setting up the machine because if I get it, people ask me questions when I'm visible, right? And then I go answer their questions. So I was setting up the machine. So I put the special fixture in the vise. I put the vise on the table. I put the bolts in the vise. Someone asked me a question. I went and helped them answer their question. I went back to my office, got my coffee, went home for the day. The next day, they come in to do ME1800 labs. They go over, hey, the fixture's all set up. We're good to go. They start running labs. And they must have made like 10 parts trying to figure out why they weren't round. Because the vise had enough mass, there was enough inertia that it pretty much stayed in place. But it would slide a little bit sideways, back and forth each operation. And so the parts were sort of the right shape, but none of them were round. And they're checking the program, they're checking all kinds of things. And they finally come to tell me, and I'm like, I don't think I ever put the bolts in that vise. So yeah, so we want to counteract machining forces. We want to orient the part. We want to locate the part. And I would say that those two things are two parts of the same thing. So we want to locate it in space. We want to fix the orientation. And we want to keep it from moving. So we don't want the part to move relative to the table that it's fixed to. So sometimes we do want the part to move because it's fixed to the moving tables, right? But we want it to stay fixed in that location on the table. All right, so that's good. That's why we fixture. How can we do it? How can we fixture in CNC machining? Yeah. Say again? A clamp. Okay. Clamp can have many meanings. And I think clamp is the overall of several of these things. So what types of clamps can we use? Yes. We could use a vise. Is that the right kind of vise? It's crappy chalk. Too much machining force. How do we reduce the machining force? Yeah. We could, but what's the easiest way? We don't really directly control the friction in our machining operation. We reduce the normal force, right? So, but we don't directly control that with our feed speed, depth of cut. The things that we can quickly address are feed speed and depth of cut, right? So what should I do? Speed? Feed? Either feed or depth of cut. Usually I depth of cut first, then feed. That's the easiest ways to reduce the machining force. Okay, so vise. Is that the right kind of vise? Yeah. Okay, good, because I always mix those up. What else? What else could we use? And we've used vices in class, right? And have we exclusively used a vise in class? I think one time, yeah.
We use the chuck on the lathe, whatever that is.
We use both the 3-jaw chuck on the lathe, and that's that one where we've got these. So if we're looking face on the chuck on the lathe, there's these 3 things here. And they move in and out like this together. And so that's closed with hydraulic pressure. So that's a method of clamping. What else have we used in the lab? Either in the lathe or the mill.
For the initial engraving, we had that hydraulic collet.
We had a collet. And so you guys know how collet works? Right? You put the thing in, you press the button, and it was tight. All right, that's how it works. At some level, that's actually all you need to know. The rest of it's like, do I need to know how electronics work?
Not really.
I need to know how to operate the power switch. Unless I want to be an electronics designer. But we should understand more about how collets work. So the collet was that round sleeve that we slid our workpiece into. You guys remember that? And we in the tooling lab. Who's done the tool assembly lab? A few of you have. All right. So we use collets to hold. So we fixture workpieces and we fixture tooling. Does that make sense? Both of those things get fixtured in our CNC machining. So in the tooling lab, we use collets also. So the collet, if we look at a cross section of it, the collet will have some taper, and it will have a hole of some diameter down the center. And so say this is a 3/8 collet, then this will be 3/8 nominally, a little bit, maybe just a hair over 3/8, so that our 3/8 inch tool can fit in here. If it's a tool or if it's a workpiece in the lathe, so that our workpiece can fit in there. And then we have something that this collet goes into called a collet holder or a collet nose. So on the lathe, we'd call it a collet nose that also has a taper on it. And we have something that pushes the collet this direction or pulls it in that direction. Right? So you could have at the bottom of the collet, there could be some threads, and those could be connected to something that pulls it. Or we could have in the mill example, this will be a little bit longer here, we'll have some sort of a nut that pushes down, so there's threads on the outside here and threads on the nut, and that pushes the collet down. What holds, in both cases, what holds the tool in the collet or what holds the workpiece in the collet?
Friction.
Friction between the tool and the inside surface of the collet. Now, in the tooling lab where you assembled the tools, there was a right and a wrong way to assemble those collet nuts before you put them in. Anybody remember? So the collet usually clips into the nut somehow. There's a spring clip or something like that, so that the collet gets attached to the nut. That way, because right now, if you just push it in with sufficient force, you can unscrew the nut and walk away with the nut. That collet's staying in there. Because there's not just friction here, there's also friction here. Right? That's staying in there until you get it out with some big hammer from the other side. So that clip pulls it back out. Okay, in the lathe, we've got collet chucks. They screw into a hydraulic tube. The tube gets pulled back and forth like this to operate that. So friction holds it in place. What holds your workpiece in the vise? If we put our workpiece in the vise, what holds your workpiece in the vise? Yep. So there's pressure applied by clamping the vise jaws if we remember to turn the handle. What does that pressure do? What is the pressure? Pressure is the normal force. So keeping your part from falling down, there might be the bed of the vise, right? That's pretty substantial. The part's not going to go through that. Parts don't usually go through stuff unless you push hard enough. Or we've got our parallels next to it. We're more likely to go through the parallels than we are to go through the vise. We could broach our part by pushing it down through the parallels. So what keeps the part from coming up or moving along the jaws of the vise? So let's neglect gravity. You could say gravity keeps the part from coming up. Right? Let's forget about gravity because we could mount our vise on the side, and then gravity's hurting us. What keeps the part from coming up? It's friction, right? Friction is our friend when we're fixturing. We like fiction. We like fiction too. I'm going to close the whole thing. Go back. Yeah, you guys can watch this video yourself. It is kind of cool. All right, we'll watch this one very quickly. Hey, this has sound. Has a little bit too much volume, though, I think. Insufficient clamping force?
Yeah.
So what do you think the friction coefficient is between butter and vice jaws?
Pretty low.
When we want to increase our frictional force, what's our option? Change the friction coefficient and change the normal force, right? So let's see what happens when we change the normal force. Like you can almost see it if you're looking close already. We squeezed the butter too hard. We caused the butter to fracture because of the normal force. This was fun, actually. Oh, I didn't want to stop, though. I wanted to move on to the next slide.
Does it butter your toast?
You could. How do I just move it? All right. There, now we're on the next slide. So how do you know what friction coefficient is? Look it up in a table, right? Engineers use reference materials, so we need to know the friction coefficient. We'll look it up in a table. Here's some common ones. And so we do a lot of aluminum machining in the lab, and we get a lot of steel vice jaws in the lab. But aluminum on aluminum actually is a better friction coefficient, huh? You know, friction coefficient can be above 1. Right? It's not one of those numbers. It has to be between 0 and 1. So friction coefficient can be higher than 1. What do you think the friction coefficient between your car tire and the asphalt pavement is? Anybody? I mean, not on a day like today. Could be 0 today. It's about 1 point something. 1.5, 1.6. Something like that. It's about the same as aluminum on aluminum, maybe. That was dynamic is 1.4. What's the difference between dynamic and static friction coefficient? Quick, somebody. Yeah. Right. So we have a static friction coefficient when we're not moving. Right? How big is the friction force? How big is the friction force right now on that part? Yes. 0, because it's not trying to move, right? Now what's the friction force? Something greater than 0. Yeah, all right, mg sine theta. So 10 times something, right? So static friction, now what is it? Theta's bigger, right? Is it moving? Okay, I can't tell from this angle. Right, and then finally, it moves. Right, and so after it starts moving, it becomes dynamic friction. And static is usually higher than dynamic, but not here on the aluminum one. Interesting. Do we know what this is? It's a turbine blade for some sort of a jet engine, but they don't normally have this. I don't think it's lead. They don't normally have this other bit of metal around them. So they made the turbine blade, but then they needed to do finish machining on this end of it. And they needed a way to hold onto it in the vise. So they took the turbine blade and they put it in molten metal in a casting, let the metal solidify around it in this boxy shape here. And now they have a surface they can clamp on in a vise to do their finish machining on this side. And then when they want to get it out, they'll put it in a furnace and melt away the other metal, because this metal has a lower melting point than the metal the turbine blade's made out of. Fixturing. So we used a vise, but we had to do some other stuff first. How else can we fixture stuff for CNC machining? we could bolt the two things together, right? So we have to have holes first in the thing that we're going to cut. We could put holes in our stock material. We could bolt it down to the bed of the machine tool. How else could we fixture stuff? There's another clamping tool actually that you could do where you've got, so here's my workpiece side view, here's the table of the machine tool. I could put a bolt down here that goes into a hole in the bed of the machine tool, either a threaded hole or we've got these T-slots that you can put a nut in the bottom of. So I could put a bolt here. I could put a strap across here. My bolt going up through here with the head. And then something over here to support that side of it. I could clamp my part down by using a strap. Does that make sense? How else could I fixture parts in a CNC machine? Carpet tape. People use carpet tape all the time to hold stuff down. How else? Let's go on a roll. Yeah. So, what's that?
Like basically super glue.
Superglue. Yeah. Oh, yeah. So superglue. People use superglue all the time. I use superglue all the time to fixture parts. It's especially good if they're dissimilar materials. So one of the things I fixture is solid carbide, silicon carbide. But I really like to hold it with a magnet because all the machine tools I own have magnetic fixturing built into them. So I'd really like to hold my carbide part with a magnet, but carbide's not magnetic. I superglue it to a piece of steel. The steel is magnetic. I put that down on the fixture. It's actually, there's operations where the operator walks over, puts the part sort of in the middle of the table, presses the start button and walks away from the machine, comes back 4 hours later and the part's finished. Because it's got probes built in, the probes go over, and as long as it's close to the center of the part, it'll work. So, and the best thing about this is steel has a fairly high thermal expansion coefficient. And silicon carbide has almost zero thermal expansion coefficient. So when you want to separate them, you could put it on a hot plate for a few minutes. The steel gets bigger, you pull it off, it breaks the glue. Or you can stick it in the freezer. The steel gets smaller, it breaks the glue, you can pull it off. Don't even have to use heat. Superglue is cool. I like superglue. Now, if you superglue the piece of aluminum to the piece of aluminum, the freezer trick is not going to work because they're both going to grow and expand the same. The heat will still work because you can melt the glue, but then you breathe the glue fumes. So you can glue it down. We also use wax the same way. We'll put a layer of wax on the two surfaces and wax them together. So you can attach one thing to another. I could attach I don't have to use a magnet. I could have a plate that has bolt holes in it that I glue my part down to and then bolt the plate down. We use magnets. What else? Clamps. This is pretty common. Yeah.
Try welding.
You could weld the part on and then grind the weld off later. It's probably about as drastic as this, but sometimes that's what you have to do. All right, so there's lots of ways we can fix your stuff, but friction is usually how we do it. And we talked about stress and strain. What time is it? Okay. All right, we talked about stress and strain before. We talked about the fact, we'll skip through that. We talked about the fact that we squeeze our thing. Now, why don't we cut plastic in the CNC machines and Washburn shops much? Yes. Nope. It easily deforms, which makes it a pain in the ass to cut. Because the way you fix that is more normal force, or the way it's low friction and easily deforms. Normal force overcomes the low friction, but then you squeeze it like this and you get parts in the wrong shape. Yeah. The chips don't break very well, and also when people want to machine plastic, they usually want to make some smoothie shape out of it. I don't know why. But when you make those smoothie shapes and you're doing a surfacing operation, which we're going to talk about this week in lab, I guess, you make little tiny chips. The little tiny chips get through the filter in the coolant system. They get through the coolant pump, no problem. That pump can pump anything. But they don't usually get through the elbow, up inside the spindle sheet metal, that turns the direction so that it sprays down and that elbow gets clogged up, and then you got to take all the sheet metal off. You got to take the little elbow out and clean the chips out of it. So that's why we don't like to cut plastic. And it does this very well. In the lathe, we also have an issue. So what direction is the cutting force in the lathe? Some of it is directly opposite the direction of interaction, right? Straight up. Applied off center a little bit, but straight up. And some of it is back into the part. But it's pretty much all trying to bend the part. Does that make sense? So if we're applying a force at the end of our part and holding it at the other end, it always bends a little bit. We may not always be able to measure how much it bent, but it always bends. And if we want to understand that, we can understand something about the material properties. But if I'm doing that, so if I'm holding it over here, and here's my part before I start cutting, and let's say here's the part that I want, right? So here's my depth of cut that I want to do. As soon as the tool comes in contact, there's going to be a cutting force in this direction, right? Does that make sense? So what's the finished part going to look like? Is it going to look like that? Or like that? Let's call this A and B. So is it going to be wider the further away from the chuck we are, or is it going to be skinnier? Because it's not going to be the same. As soon as we start deflecting, the part's going to change size. Who says B? Who says A? Stand up if you said A. Who else said A? Take a bow. Why is it A?
Because it'll bend away from the tool at the end.
Because the workpiece bends away, which makes the depth of cut smaller. When the workpiece bends away, the depth of cut gets smaller. So the part gets bigger at this end. The closer we get over here, the less deflection we're going to get. In fact, it depends on the length cubed, right? So our deflection equation here, deflection, that's this delta max, is P. What's P? That's the force. That's the resultant force times the length cubed. So if we want to have less deflection, we can reduce the force. We can reduce the length. 3 times E, what's E? Elastic modulus, and that depends on the workpiece material, right? And I is the area moment of inertia, which for a circle is pi r to the 4th over 4. So we can make r bigger. That would make deflection smaller, right? Because we make I get bigger when r gets bigger. That's twice. All right, so we have less deflection that way. And if you know these things, you can calculate how much deflection you get. All right, this is the last thing. How would you fixture that part to cut it in the CNC machine? Anybody get an idea? When the students came and wanted to make this part, the first thing I said was, could we make it a different shape? Right, because the one that would be easier to fixture. So what's the hard part about fixturing this? It's tapered here, right? It's kind of skinny compared to its length, so it'll deflect to plenty. See, I think I have a picture of how we did it. I'll get used to this interface pretty soon. Yeah. So first operation, I cut like that. Then we cut the tabs off with a bandsaw. Oh, there's that operation. We cut the tabs off with a bandsaw, stuck it out of the fixture a different direction with clamping on these two sides, made the little pocket there, and then stuck the other end out and made the little hole. So there's an innovative way to cut the part. Leave some features in your stock material and come back and machine them away later. And we do that in the lab with the base, right? We hold on to that bit, we make the contour we want, we flip it over, and we face off the part that was left over. Same idea. Okay, schedule and group project. We got like 5 minutes left? Perfect. So this weekend, I'm going to use my oops. Because this weekend you were supposed to have a quiz, right? Yeah, but you didn't have the quiz. Yeah. And so I fixed it. See, which week was this? Is this week 4? See, I moved it. It's not there anymore. It's down here at week 6 now. We weren't going to have one on week 6. We were going to have one this week. So I fixed that. And we also changed the dates. If we look, actually, it's probably easier to see it in the syllabus. I actually changed the due dates for group project number 2, which was going to be due, I don't know, Sunday, something like that. That's going to be due a week from yesterday midnight, so 1 week from now, roughly. Sunday quiz, week 4, moved to week 6. We're also changing the due date preemptively for group project 3, so you don't have 2 group projects due on the same day, because that would kind of suck. So, and also, see here in the syllabus, you guys probably read this, but I'm just going to remind you, so late assignments, right? If for a medical reason you had to hand in your homework late, unless there's like 9 of them in a row, I don't need a note from your doctor. I'll take your word for it that you had a medical issue. I believe you. If you had an emergency and needed to hand an assignment late, now my cell phone battery died isn't an emergency. You fix that with planning. But if you think that something happened that you should get consideration for, just let me know what it is. And oops, if you just had a bad day and didn't hand in an assignment, you can get consideration for that also. All you have to do is say, oops, that one was late. So I'm using my oops this week. So I have shifted the assignments to later due dates and using my oops. If you want to receive consideration for a late assignment, fill out this form. It's not dangerous, I promise. Which assignment do you want to receive consideration for? I don't know. Let's say Sunday quiz 3. Is that the one that we didn't have yet? Okay. Why? My roommate had to go to the hospital. See, there's a good emergency one. Had to bring my roommate to the hospital. Right? My dog ate it. That's an oops. Say why. Say next. Submit. Your response has been recorded. At the end of the term, I'll go through the submissions here and update the grades accordingly. In Canvas, it should automatically be taking points off for late submissions at 10% per day. If you've already spoken with somebody about not having late points, we think we gave those back to you, but check. And if you do have late points off, whoever it was you talked to will go fix that. Okay? I want everybody to get an A in the class. I want everybody to get an A in the class, but I have to have something that justifies it. Otherwise, I would just give you all A's now, and you can show up if you want to learn.
Professor, just going to preemptively apologize. Instead of filling out that consideration form, I directly emailed you. So.
Just go fill out the form.
Yeah, I'll have a session tomorrow. No class.
Oh yeah, no class tomorrow, but there is a help session for the group project. No, I won't be in lecture tomorrow. The TAs will be in lecture tomorrow helping you with the group project, which is posted on Canvas. So go to the normal class time, but it's about group project 2, whatever it is, number.
So Friday quiz number 1.
Yeah. I don't think we marked anybody late for Friday quiz 1.
Okay.
Or maybe Friday quiz 1.
There's one thing.
Yeah, no, Sunday quiz 1 we didn't mark anybody late for. But Friday quiz, submit the form.
It wasn't late. And I got a 4.5 the first time. The third attempt seemed to last for like 6,000 minutes for whatever reason.
You never click submit, maybe?
I'm not sure. And it kept the one. Like I never submitted it.
I don't know.
One. So just fill the form.
Fill out the form and click other and explain.
All right. Work.
Unless you want your question on camera.